Hello, this is Philip Myers of PEMI Consulting. Welcome to the API 656 task group. I present this tutorial to get everyone up to speed on what exceedance probabilities and mean recurrence intervals are and how they're computed. This is important because the building codes use these ideas to establish criteria for both buildings and structures to survive various loads such as earthquakes, wind, flooding, tsunami, rain, and other natural hazards which can lead to NATEC events. Because petroleum and chemical storage are the lion's share of NATEC disasters, understanding how these criteria are established is important in developing new and better assessments, methods, guidelines, and practices that we'll hopefully include in API 656. But let's try to have a little fun with this, starting with some gambling. Chevalier de Mere was a gentleman gambler in France. He had two games. The first game was that he would bet even odds on getting at least 1/6 on 4 rolls of a fair die. He correctly thought that the chance of getting a 6 on one roll was 1/6 or 1/6. But he thought that in 4 rolls the probability of getting a 6 would be 4 times as much, or 4/6, which simplifies to 2/3. This was not correct, but he did okay and made money on this game anyway. The second game was to bet with even odds on getting at least a double 6 on 24 rolls of a pair of dice. He correctly believed the chance of getting a double 6 in a single roll of a pair of dice was 1/36, because there's only one way to get 2 6s on a single toss of 2 dice and a possible total of 36 outcomes. This is easily seen since each of the 6 numbers on the first die can combine with the other 6 numbers on the second die so that the product is 6 times 6, or 36 total outcomes for the pair of dice. But he thought that the chance of getting 1/6 would be 24 divided by 36, or 2/3 for the 24 rolls. He was, of course, wrong on this bet and he was losing money. Bemoaning his losses, he turned to his friend, Blaise Pascal, who started a dialogue with Pierre de Fermat about this problem. Together, they contributed to the initiation of the whole field of modern probability theory with this dialogue. So let's see why the first game was profitable. There are 6 possible outcomes for a die, 1 through 6. Therefore, the probability of no 6 on a single toss is 5/6. In 4 rolls, we can multiply the 5/6 4 times, or take 5/6 to the 4th power, which gives 0.482253. We can multiply probabilities because of independence, which we'll talk about later. If the probability of getting no 6 in 4 rolls is about 48%, then the probability of getting at least 1 6 is the complement, or 100 less 48%, which gives 52%. Therefore, on average, he would win 52 out of 100 games. This is much less than his original estimate of 2/3 or 67% wins. On the second game, the probability of a double 6 is 1/36, so the probability of no double 6 is 35 divided by 36. Therefore, the probability of no double 6 in 24 rolls is the fraction 35/36 raised to the 24th power for the 24 rolls. This works out to 0.5086, or 51%. Therefore, the probability of at least 1 double 6 in 24 rolls is 100% less the 51%, which is 49%. Out of 100 games, our friend would win 49 games. Okay, it's time to get down to business. There are 3 axioms of probability upon which all modern probability theory and statistics is founded. The first axiom says that the probability of an event is greater than 0. The second axiom says that the probability of all events in the sample space, which is essentially all possible outcomes of an experiment, is equal to 1. From these 2 axioms, it is easy to see that an event probability is in the range 0 to 1 inclusive. The impossible event has probability 0, while the certain event has probability 1. The third axiom says that the union of probabilities for disjoint events, meaning that they do not overlap, is the sum of their individual probabilities. From the first and second axioms, it's easy to prove that the probability of an event in which A does not happen is called the complement of A and is indicated with a superscript C and is equal to 1 less the probability of the event A occurring. We used this principle in Chevalier-Demers' problem. Finally, there's independence. A useful way to think about independence is to consider two events A and B. If the outcome of event A tells us nothing about the outcome of event B and vice versa, then the two events are independent. Independence is important because it usually simplifies the math. Probabilities for independent events can be multiplied as we did in the Chevalier-Demers problem. Recall that whether or not you roll a 6 will tell you nothing about the outcome of the next roll, and each event or trial roll is independent of all others. Suppose that we are interested in earthquakes that equal or exceed some magnitude of ground shaking. Let's call this event E. If we consider our basic time unit as a year, then the annual probability of exceedance P of E is equal to little p. The MRI, or mean recurrence interval, can be taken approximately as the reciprocal of P. We know that if in a given year E does not happen, then by the complementation rule, the probability of not E is 1 minus P. Because earthquakes are independent, we can use the multiplication rule for independent events to find the probability of no event E in n years, which is 1 minus P raised to the nth power. Then the probability of at least one event in n years, again by the complementation rule, is 1 minus P to the nth power. This formula shows up everywhere in ASCE 716 and is in all of the building codes. You can see from the table that the relationship between return period and annual exceedance probability is reciprocal. So let's solve a few problems. Given a 2% exceedance probability, what is the exceedance probability P of E for a period of 50 years? Second, given a 1% annual exceedance probability, what is the exceedance probability for a period of 30 years? Using our formula for the first problem, the probability of no event in 50 years is 36%. For the second problem, the probability is 74%. I chose this problem because for flood insurance, the basic MRI is 100 years, and the flood insurer hopes that no event in 30 years occurs, which is the average mortgage lifespan. This is a clipping from the wind load provisions of ASCE 716. Footnote 5 has minimal explanation for what the AEP is for an MRI of 300 years, but armed with our knowledge, we can now understand this footnote. In the formula, we plug in the 0.00333, which is the reciprocal of the 300-year MRI, which we know is the annual probability of exceedance. The formula outputs 15%, which agrees with the footnote. This is a clipping from the commentary about wind in ASCE 716. Here they give the formula. I wanted to include this to show that finding the annual exceedance probability P sub A when the MRI is known is shown here. Also, when we're taking longer than an MRI of 10 years, it's sufficient just to assume that the MRI is equal to 1 over P sub A. Well, I hope this all gets us on the same page because we have to work with natural disasters, and that requires an understanding of these ideas. Thank you.